It is really starting to feel like this AI thing is getting crazy, but today I found a paper, and out of all the crazy things I could have talked about, I just wanted to hone in on it because I haven't seen anybody else cover it, and it felt like a video that might actually just give you guys some unique insights into some corner of AI that I could kind of like actually, help educate you on. Today we're going to be talking about embeddings. It's okay if you haven't heard that word before or don't know what it is, I will go over it, but if you're wondering about how something like ChatGPT, which is a large language model, actually performs the magical abilities of writing the way it does, embeddings are a key component. Component's not even the right word, it's more of a translation, because in our world, we write in a language, like English for me, but the computer doesn't really want that. Like what it wants is math, it wants numbers. And when you change something like an English sentence into numbers, you can do it in a lot of different ways. And embeddings kind of is that big concept that encapsulates the way you do that. Now, practically speaking, what you're doing is actually taking individual words in the English language or word phrases, which we call tokens, and you embed them into a number. And you usually put that number in some kind of an array, which is the same thing as like a list. And in a really fascinating, fundamental way that mathematics works, you can actually take lists and think about them as coordinate systems and multi-dimensional coordinate systems, and you can actually do distance measurements on these things. And this is why it all is magic and it works, and it doesn't necessarily have an intuitive way to explain it. But here's where it gets crazy, because the embeddings themselves were actually just maps that take you to the words, and that's how you do the mathematics. You kind of do this probabilistic thing and you pull out what the predicted next word is, and you make these amazing sentences. However, it turns out that when some researchers from Cornell decided to look at the actual embeddings themselves to see what kind of other information there is that you can pull out of a system, not just doing the mathematics and looking for the text, they found some big privacy risks. And that's what I'm going to talk about in this video. I'm going to break down this research paper called Text Embeddings Reveal Almost as Much as Text. And to do that, we have to have a slightly philosophical conversation about what it is that they're actually capturing with this multi-dimensional data, these big lists, these arrays of numbers that represent words that translate. What is it that they're doing? Why do some words have a different distance between one another, and why does that matter? Well, the answer is meaning. Honestly, the meaning of a word is captured in the distance. As incredible as that is. You'd think a word or a sentence has more meaning to me than someone else, and it's kind of subjective, but when you look at the entire corpus of like the English language or any language, the meaning is embedded in the way people communicate, and that's actually what's captured in those distance measurements. And over the years, AI researchers have come to different patterns, like different architectures that they can use to capture this meaning. One of the most famous ones is called word-to-vec, another one called glove or BERT. All different architectures that tried to capture meaning in different ways and had various success at different times in the past. And remember, not all word embeddings are just like ChatGPT LLMs. There was also recommendation engines, sentiment analysis, language translations, and other types of semantic relationships between words. And we use the word semantic when we're talking about like the meanings of a sentence, a paragraph, a language, instead of like syntactics, which is when you're actually talking about like how the language is constructed, the syntactics of the language. And they both sort of had their time in AI history, but syntactic analysis is much more of like an early 2000s kind of thing, and now semantics is really like what's kind of taking over. In fact, before there was even embeddings, there were things called bag of words model that worked strictly on that syntactic analysis. And they did some things really well, but they failed to capture the complexity, the nuances, the sort of double entendres and weird stuff that we do in English to communicate that works in our heads but doesn't always make sense when you try to map it out. When embedding showed up, it was like a real boon to artificial intelligence. Like stuff started working way better. So these embeddings, usually sometimes called a vector embedding because they look like a long list of numbers, just think like number, comma, number, comma, number. They come in a couple different forms. You can have sparse or dense. Now sparse is kind of good for classification, meaning you'll have like a big array of numbers, like think of a ladder with like spaces between, and most of them are zeros, but the one that you actually want, like if it's cat or dog that you're trying to classify, is actually activated as 1 and the rest are zeros. Or it can mean something else where like a few of them are activated, but a lot of them are zeroed out, which can be computationally really helpful, so there's still a place for this kind of sparse representations. But realistically, all these big breakthroughs, all the ChatGPT stuff, they are dense embeddings, meaning you have this huge list of array, it's capturing all this semantic meaning, and it's doing it with numbers, like every rung on the ladder has a number in it, and that has some kind of representation. It can be negative, it can be positive, it can have decimal places. That's what's giving it so much nuance into how like all these things are mathematically positioned next to one another. Using vectors or arrows, if you kind of remember, like think trigonometry when I'm saying this kind of stuff. Because a lot of what ChatGPT is doing when you ask for a question is like doing something like trigonometry, except it's in multidimensional space, but it's a distance measurement in terms of like angles and things that are like adjacent to one another or perpendicular to one another. So for example, you might have some long 300 dimensional vector, like brackets, 300 different numbers, each with commas next to them, each with decimal points, and that would represent a single word or token in the English language. And as these big training runs go, these big supercomputers are looking at lots and lots of data, like all of Wikipedia and the entire internet. They're tuning where each word is located on this huge 300 like rung ladder, basically. Or the longer that you make these vectors, the better the model gets. And that's why the real cutting edge models require hundreds of millions of dollars of compute to make. But now let's get to the crux of the argument, the big wow moment, and that is what these Cornell University researchers did. They have created something called vec to text. Remember the text to vec model, which I said was like really groundbreaking in the early 2000s? Reverse those two words. And now you have the first model that's a solution to something called the inverse challenge. This is a groundbreaking development that essentially reverses the process of a text embedding. So remember, text, English words in a sentence, each token or word phrase is converted into a number on a long array. That's the embedding, and it's positioned to somewhere. Now, these kind of embeddings have traditionally always been thought of as like a one-way conversion, sort of like running something through a hash function. Like once it's on the other side, you can't start from that and then go back to the original number. Like cryptocurrency prime number mathematics or something where you can go one direction, but you can't go back the other way. And that has been an important aspect of the security and privacy and safety of these models. In a lot of cases, you don't want somebody to be able to just take the vector embeddings and then go back and figure out what the original data was. However, vec2text has changed that, and it's not perfect, but it's accurate enough that we should know about it, be worried about it, come up with solutions for it, or at least understand that systems aren't secure in that way anymore. So this new model generates a hypothesis about what the original text could have been by looking at the embedding. And then the researchers, which on the training data actually knew what the embedding was, told it what it was, and it corrected its error the same way all of these systems learn to get better and better at going in the reverse direction. And at least according to this paper, 92% of the time, these researchers are able to actually recover the original text in 32-bit embeddings. I mean, that's crazy, and this definitely raises some serious privacy concerns. Because if the text embeddings can actually recover the text, then we need to treat the original text very carefully. Like if you trained it on your sensitive company data and everyone else is using it and you're thinking, oh, they can't like go back in time and figure out what that original data was, with 92% accuracy, they probably can, right? And I, with everyone else, have been like really caught up in this whole vector database thing. And these are databases that don't use regular tables, they use vector embeddings. Super awesome in many ways. It's kind of the way that we can start having long-term memory in some of these ChatGPT like large language models. But now if these vector databases, which are really interesting and they have super powerful use cases, can be reversed, that's a problem. Like I went to this AI conference a few months ago, and in the exhibit hall where all the booths are, I saw so many different like vector database companies, and some of them were targeting like medical and serious business. And I'm like, whoa, is this reversible? Like that's personal information and clinic notes and things like that. Lucky for us, the same researchers also have some thoughts on how you can actually prevent some of this to try to make it more secure. And they recommend a basic defense strategy of adding something called Gaussian noise to the embedding when you put it in there. So a bunch of extra information that isn't relevant but would throw off a system that was trying to do it in reverse. And they showed how the retrieval process should be just about the same amount of time, but that would prevent and make it much harder to have a high accuracy when you're going in reverse from the embedding to the text. But that's by no means like a complete solution, and I can just imagine a better model that's doing vec to text, just figuring out how to get around the Gaussian noise, because that's what these systems are really good at. Another thing that makes this more secure is that 93% recovery rate isn't for like every size model. As the models become super big, like these big trillion parameter models, that kind of a system is going to be much harder to use in any kind of efficient manner. So just size does make things more secure, but it's a reminder that in this world of AI, like nothing seems static. Like you think something's safe or it works one way, boom, like overnight a new paper comes out and it's like, whoa, this is not how everybody in the industry assumed this worked. And if you're down to embed the subscribe button, do that right now. Help me get to 8,000 subscribers. I appreciate you.